derivative of a function measures its rate of change. Imagine a quantity denoted by variable y which is continuously changing. But how it changes is controlled by another quantity denoted by variable x. We can say that the variable y, called the dependent variable, is a function of the variable x, called the independent variable. The function f tells us how the value of y changes with the value of x. The derivative of a function at a particular value of x tells us the rate of change of y with respect to x at that particular value of x. That is how fast or slow the value of y changes with respect to x. In our previous video, we saw how to find the derivative of a function. The whole process is summarized like this, and it's called differentiation. This ratio here is called the average rate of change between two values of x, which are x0 and x0 plus delta x. If delta x is greater than 0, then x0 plus delta x will be somewhere here on the x-axis. Then this ratio is the slope of the secant line between these 2 points. Now, as we find the average rate in the interval closer and closer to x0, we see that these secant lines approach the tangent line at x0. This would be true even if we take delta x to be less than 0. Then x0 plus delta x will be somewhere here on the x-axis. And as we find the average rate in the interval closer and closer to x0, we see that these secant lines approach the tangent line at x0. So we say that in the limit delta x tends to 0, the average rate of change approaches the instantaneous rate of change at x0. That is nothing but the derivative of the function at x0. We denote it by putting dash like this on the notation for the function. Note that the limit delta x tends to 0 does not mean we put delta x equal to 0 in this ratio. This would result in the ratio being equal to 0 divided by 0, which does not make any sense. In this video, we will understand what this really means. Along with it, we will also explore different theoretical aspects of the derivative of a function. Consider this simple example. Y is equal to square of x. Let's say we want to find the derivative of this function at a particular value of x, say x1. Can you find this out? Actually, in one of our previous videos, we found the answer to this. We had found the instantaneous speed of an object for such a relationship between the distance traveled and the time elapsed. To find the derivative, we would first find the average rate of change. That is, how the value of function changes as the value of x changes by delta x. F of x1 plus delta x and f of x1 will be equal to this. After expanding this term and simplifying, we will get this. And after dividing by delta x, we will get this final expression. Now we know that to get the derivative, we will need to consider the interval delta x tending to 0. So we put delta x equal to 0 here and get this. It's the derivative of the function at x1. But now notice that all these expressions are equivalent to each other. So what if instead of putting delta x equal to 0 here, we put delta x equal to 0 here or here? We see that we will get the numerator and the denominator both equal to 0. But for this final expression, we got the answer as 2 times x1. So what's going on here? Why can't we substitute delta x equal to 0 here and not here? Actually, substituting delta x equal to 0 at any step here is not correct. Notice that in these steps, we are dividing by delta x. And we know we can't divide by 0. What delta x tends to 0 means is that we're considering smaller and smaller values of delta x. The values of delta x are close to 0, but never 0. But among all these steps here, delta x does not explicitly occur in the denominator here. So it's easy to see from this step that as delta x gets smaller and smaller, the average rate gets closer and closer to 2 times x1. So substituting delta x equal to 0 here is just convenient to reach this conclusion. But always be aware of what it really means to put delta x equal to 0 here. Now notice one more thing. Although we had not explicitly stated here we took delta x to be greater than 0. That is, we are finding the average rate between x1 and the values of x greater than it. But it is necessary to consider the case when delta x is less than 0. That is, finding the average rate between x1 and the values of x lesser than it. As we find the average rate when delta x tends to 0, this average rate should approach 2 times x1. So let's find the average rate in this case when delta x is less than 0. We can see the calculation for finding the average rate of change will be the same as this. But in the first case, this average rate will always be greater than 2 times x1. And in the second case, this average rate will always be less than 2 times x1. Now when delta x tends to 0, both these average rates will approach the same limit 2 times x1. Now we can conclude that the derivative of this function at x1 is equal to 2 times x1. So we see that to find the derivative of a function at a particular value of x, we have to find the average rate of 2 cases. When delta x is greater than 0 and when delta x is less than 0. Now when delta x tends to 0, if both these average rates approach the same number, then that number is the derivative of the function at that particular value of x. But consider this function now. It's called the absolute value or modulus function. These vertical bars say that the value of y is equal to only the non-negative value of x. That is, if x is greater than or equal to 0, then y is equal to x. And if x is less than 0, then y is equal to negative of x. Can you find the derivative of this function at x equal to 0? Share your thoughts in the comment section below. We will find its derivative in the next lesson. Don't forget to subscribe in order to get notified.